Hello students, topic 26 is linear planar homogeneous systems of ODEs. Now we're going to show that if R is an eigenvalue of a square matrix A with a corresponding eigenvector V, and it can be any of its eigenvectors that correspond to that eigenvalue, then the vector x equals e to the rt, which is a scalar, times the eigenvector V is a solution to vector x prime equals A times vector x. So this is a linear system, and it is homogeneous. Notice there is no plus f vector. We're assuming the f vector is 0, so we have a homogeneous linear system of ODEs. Okay, to verify that this vector here is in fact going to be a solution to this system, we simply have to plug in this vector in for the x here and the x here and see if both sides of the equation are true. So let's begin by doing x prime. X vector prime. Now keep in mind that this is a scalar and it's being multiplied by a vector v, and the vector v is going to be a vector of constants. It's an eigenvector, which is a vector of constants. And so the only t involved is the e to the rt component. So this e to the rt would multiply to every component of this vector. So just for example, if this vector was 2, 1, and I multiplied it by e to the 5t, then the vector would now be 2e to the 5t over 1e to the 5t. We would have this vector. And when you differentiate a vector, you differentiate each component of the vector. Also true for a matrix. So really, in the end, when I differentiate this vector here, I just have to really differentiate the e to the rt and then distribute that across the vector v. So the vector v acts like a constant coefficient, if you will. We just have to differentiate e to the rt. And so we get r times e to the rt, that's the derivative of e to the rt, and then times that constant eigenvector v still. So this is what we would have for vector x prime. Now let's do this side of the differential equation and do the matrix A times the vector x, and the vector x is given by this. So we can just copy this here. Here's the vector x, copy, paste. Okay, now e to the rt is a scalar. And so we have a matrix times a scalar times a vector. So this scalar can distribute either through the matrix or through the vector, or distribute all the way through to the other side, which is what I'm going to do. I'm going to pull that scalar all the way to the very front. So we just have the matrix A times the matrix, or the vector V. But because V is an eigenvector of this matrix, when you multiply V times the matrix A, you should get the eigenvalue times the eigenvector. So this part right here is the same thing as R times the eigenvector. So this allows me to say that we have e to the rt times the scalar r times the eigenvector v. And since that's a scalar and this is a scalar and this is all multiplication, I can rearrange these any way I want. And we can just write that instead as r e to the rt as a scalar times the eigenvector v, which was the same thing as our x prime, our x vector prime. So the key, of course, was this step right here. Because v is an eigenvector corresponding to eigenvalue r, that the matrix A times v will be r times v. Okay, now and this was true, by the way, up here for any dimension system, 2 by 2, 3 by 3, etc. But now we're going to focus this topic mostly on planar. Planar systems are systems that are dimension 2. So suppose that x prime is equal to ax is a planar system with constant coefficients. So it is homogeneous, it is linear, it is planar, dimension 2. So this x vector here just stands for x and y. It's a 2 by 1 vector. And also the matrix A is constant coefficients. So no t's in here, so this is going to be autonomous as well. So only constants in the matrix A. If A has two real distinct eigenvalues, R1 and R2, with corresponding eigenvectors V1 and V2, and these can be any of the infinitely many eigenvectors that correspond to these eigenvalues, then the general solution to the system is given below. So we would take an arbitrary constant times e to the first eigenvalue times t times any of its corresponding eigenvectors plus a second arbitrary constant times e to the second eigenvalue times t multiplied by any of its eigenvectors. And the v1, v2 can be any from the infinitely many eigenvectors that correspond to any one eigenvalue. Okay, we're going to find the general solutions to the system below. Now, this is actually a matrix for which, in our last lecture, we've actually found the eigenvalues and corresponding eigenvectors, but I'm going to go ahead and do it from scratch again. So we'll begin by finding the eigenvalues. So to set up the eigenvalues, we want to remove r from each of the main diagonals and then find the determinant and set that equal to 0. So absolute value sign, that means we're doing a determinant of a matrix. We do -4 and remove r. Now the non-main diagonal, the 6 and -3, stay the same, but then also remove r from the 5. And then we're doing this determinant, and we want that determinant to be equal to 0. Now we do the product of the main diagonal. So we have -4 minus r times 5 minus r. And then we subtract the product of the other entries, these entries here. And the product of 6 and -3 is -18. So we're subtracting -18, so we've got to add 18. Then we do some foiling here. We get -20 plus 4r minus 5r plus r squared plus 18 is equal to 0. This is a quadratic equation. We get r squared minus r minus 2 is equal to 0. So r can be, let's go ahead and factor first. R minus 2 and r plus 1 is equal to 0. And so our two eigenvalues are 2 and -1. Again, this was done last lecture. Now we want to find any eigenvector that corresponds to each eigenvalue. So let's go ahead and call these R1 and R2. So let's say R1 is the negative and R2 is the positive. So now let's go for V1, vector 1. Vector 1 is any eigenvector associated with R1, which is -1. And to find an eigenvector, you really just want to find a solution to remove the eigenvalue from the main diagonal. So we're effectively trying to find a solution to, or we want to solve. I'm going to rewrite the matrix, matrix here, but remove the eigenvalue from the main diagonal. So we're going to remove -1 from the main diagonal. Removing -1 is like adding 1. So our main diagonal would become -3 and 6. And the other entries stay the same. And we're trying to solve this times some sort of vector x. It doesn't really matter what you write there, but you want this to be equal to 0. You want to find any vector here that satisfies this statement will be an eigenvector. And you don't really have to convert this into augmented matrix and then put this in a reduced row echelon form. Very often, more often than not, you can simply eyeball a vector that'll turn these rows into the 0 vector over here. In other words, since the two rows are identical, we just want to figure out what number could I multiply to -3, and how can I scale -3 and then add it to a scaling of 6 so that I get cancellation and I get 0. Well, one thing that comes to mind is that if you were to double -3 and then add it to 1 of 6, in other words, if I had doubled 1 and did not negative, but just regular 1, oops. So if 2, 1 were my numbers that dropped on here and then added, I would get 0. And if that dropped here and did the same thing, multiply corresponding entries and add, you would get 0. So 2, 1 is a solution to this system. So let's write it this way. One solution is 2, 1. So this is going to be an vector associated with the eigenvalue. Let me write it this way. So we worked with R1 equals -1 first, and this is going to be our eigenvector V1 that we're going to be working with. Now, any multiple of 2, 1 would also be an eigenvector. So you could, in theory, also put 4, 2 here, 6, 3, -2, -1, 1, 1/2. Lots of different, any multiple of this will make this system here satisfied. Okay, now, when I did this before, we found all the eigenvectors associated with this eigenvalue. But for our purposes in solving systems of linear equations, we just need to find any eigenvector associated with that eigenvalue. So let's move on to the next one. Our second eigenvalue is R2 is equal to 2. And so we want to solve, I'm going to remove the eigenvalue 2 from the main diagonal, so subtract 2 from both of these entries. And that's going to give me -6 in the 1, 1 position and 3 in the 2, 2 position. And the other entries do not change. So we're trying to solve this system. And you can write this in augmented matrix form if you want. It doesn't really matter. You can write it like this and say this is what we're trying to solve. And of course, one way to do this is to put this in reduced row echelon form. But really, you just need to think, is there a vector you can put here and here, like 1 and 1, and then drop it down, multiply and add, and get 0 both times? And if that's the case, 1, 1 clearly will work here. Then we have found an eigenvector. So v vector eigenvector 2, one solution to this will be the vector 1, 1. Of course, any multiple of this vector would also work. 3, 3, 5, 5, 10, 10. Let's just go with the most simple, basic ones. Doesn't matter which one you pick ultimately. So we've found the two eigenvalues. They are real, they are distinct, and we found an eigenvector corresponding with each eigenvalue. Now all we have to do is construct the general solution. So our general solution will be any constant, C1, times e to the first eigenvalue times t, so e to the negative t, because we're going with r1 equals -1, and then times its eigenvector. So 2, 1 was the eigenvector associated with that eigenvalue. And then plus another constant times e to the second eigenvalue 2t, and then times any of its eigenvectors, so 1, 1. And this forms our general solution. Okay, the next slide we're going to do a particular solution. So we're going to give some initial conditions, and we're going to find what C1 and C2 are. Okay, so this is the same system, but now we have an initial condition. Let's read these instructions right here. Find the particular solution to the system below with the given initial condition. Use technology to plot each component of the solution against T and then against each other. In other words, make a phase plane portrait. Okay, so we're going to begin with the general solution, and the general solution was x equals some constant C1 times e to the negative t times the vector 2, 1, plus a second constant e to the 2t times the vector 1, 1. Just double check I copied that correctly. Looks good. Okay, now we want to plug in 0 and create a system of equations here. And by the way, you could write this general solution the following way. You could distribute the scalars through the vectors and then combine the two vectors. Distribute, and then combine the vectors. So I could write my general solution this way. It would be 2c1 e to the negative t plus c2 e to the 2t. And the second component would be c1 e to the negative t plus c2 e to the 2t. So here's your general solution written as a 2x1 vector. And by the way, all this ultimately represents a 2x1 vector as well. And we just have to find C1 and C2 so that when I plug in 0, I get 2, 3. So that's the next thing I'm going to do is plug 0 in for all the t's. Evaluate this general solution at t0. And e to the zeros are all 1s, so we just get 2c1 plus c2 in the top entry, and the second entry is going to be just c1 plus c2. And we want this to be equal to the vector 2, 3. So this creates another system of equations that we can solve for C1 and C2. Of course, you could solve this system by doing an augmented matrix, and then row reducing to get it to reduced row echelon form and find C1, C2 that way. Or you can do substitution elimination, whatever is fastest and most convenient. I notice that if we subtract the two rows, we will cancel the C1s, or the C2s. So if I were to do something like row 1 minus row 2, what would that produce for us? We'd just get 1 C1. the C2s would cancel, and over here on the right we would do 2 minus 3, and that would give us negative 1. Now that I know that C1 is negative 1, I can easily look at row 2 and figure out what C2 has to be. If C1 is negative 1, then C2 has to be 4 in order to get that 3. So then our particular solution to this is the 2 by 1 vector. I'm going to just rewrite this effectively, but change the C1 and C2 to their values. C1 is negative 2, or negative 1, so we get negative 2e to the negative t plus 4e to the 2t. And that is our first component. And the second component, looking at this right here with the correct C1 and C2, C1 is negative 1, so we just have negative e to the negative t, and then plus 4e to the 2t. And this stands for, there's an x function, an x-coordinate function, and a y-coordinate function. So this first function up top, we're going to say dictates what x is at time t, and this second function down here will dictate what y is at time t. And we're going to use technology to plot both x and y against t here. So there'll be two graphs in this top portion, but then we are going to eliminate the parameter and do the phase plane portrait and show how the point x comma y moves as t varies, as time moves on. Now I'm going to move over here to Desmos. I've actually already typed in all of these equations so we can do this part quickly. I do have a slider here for a capital T that I just set from 0 to 2. And I'm using f1 and g1, these two functions, this function and this function here, to represent my x and y components of my solution I just found. And I'm using f1 and g1 because we're going to ultimately do 3 different particular solutions in this topic lecture. So I have an f2, a g2, a f3, and a g3 down below. But for this first problem, these are the two functions. Now, on this scale, it doesn't look like much. If I change the scale on some of the axes, and maybe separately, you start to get a sense for what these functions are doing. They appear to be approaching the same curve as we go to the right, and that curve would be 4e to the 2t, which makes sense because the e to the negative t's will approach 0 as t goes to infinity. So both solution curves approach the same asymptotic curve. And if we can zoom in a little bit more, we can get a sense for how they're different. Notice their initial 0, 3. So the purple represents the y coordinate as a function of t, and the green, of course, represents, highlight the green. The green is the x coordinate as a function of t. So at time 0, the green tells us that x should be 2, and the purple tells us that at time 0, y should be 3. Make sure we're interpreting that correctly. And then as time moves on, the x and y coordinates approach each other, meaning that the blue and red outputs approach the same value as t moves on to infinity. Now to plot this as a phase plane portrait, we do this fourth line down where I have f1 of t comma g1 of t written as a point, and I'm going to plot it from 0 to capital T, and just directly below that I have f1 of capital T and g1 of capital T. And in our notes, you should take a moment and plot these two curves here. And you can do this by importing, graph it nicely in Desmos and import it, or you can just roughly do this by hand. I'd be okay with that. Just draw some sort of curves like this and label which one's which, but you don't have to make these images perfect for your guided notes. But now we're after what would this image look like? So going back to Desmos, I'm going to hide now the depictions of the functions as functions of time. I'm going to reveal the graph for f1 g1 of t as t advances from 0 to 2. And let's zoom out and see if we can see where this curve, oh, I see the curve over there. Let me hit the home button and see what this looks like. Okay, so I've reset the scales. Let me show you what dragging t does. When you drag t, it just shows this thing being drawn as, it shows the point moving effectively as time moves on to infinity. And if you want to reveal the point, then I have this f1 of capital T comma g1 of capital T, and then you can see how the solution advances in the xy plane as time advances, as t advances. So remember, initially we were at the point 2, 3. So you can see we're at the point 2, 3, and then the solution as time advances moves off into the first quadrant like this. So our solution begins at 2, 3. We're at 2, 3. That's when time is 0, and then it did some sort of motion that direction as time advanced. Okay, let's go to the next example. Suppose, again, we have another homogeneous linear planar system, and A is constant coefficients. If the matrix A has one real repeated eigenvalue R corresponding to two linearly independent eigenvectors v1 and v2, then the general solution to the system is given below. So we have a constant times e to the rt, a constant times e to the rt, because there's only one eigenvalue this time. And these two vectors v1, v2 are the two eigenvectors that correspond to that one eigenvalue. And yes, that can happen. We'll talk about how to recognize that you get multiple linearly independent eigenvectors for one eigenvalue as we proceed with this next example. I do also want to point out that it's not always true that a repeated eigenvalue will have multiple corresponding linearly independent eigenvectors. And in cases where, for example, where we have a planar system and we do have a repeated eigenvalue, but that eigenvalue only has one eigenvector that goes with it, then we will talk about that case later at on a future topic. So clearly what's being mentioned here is not going to happen in this example. So find the general solution to the system below. So this time we're doing x prime equals this diagonal matrix times x. Let's go with find the eigenvalues first. So we're going to remove r from the main diagonal and leave the other entries the same, and remove r from the main diagonal, do the determinant, and set that equal to 0. Well, when I do the determinant and I multiply the main diagonal, it's going to just be the main diagonal minus 0, so we just have to multiply the main diagonal and set that equal to 0. And all the negatives will cancel. This is going to be effectively doing the same thing as 2 plus r times another 2 plus r. It's going to be 2 plus r squared is equal to 0, so r is equal to negative 2, and it's repeated. And now we want to find the eigenvectors that are associated with this repeated eigenvalue. Okay, so let's now rewrite. We effectively want to solve. I'm going to rewrite this matrix. I'm going to remove negative 2. Removing negative 2 is like adding 2. So I'm going to add 2 to the main diagonal. Notice that just zeroes out everything. So we're effectively trying to solve this system. Now you can see that it doesn't really matter what vector x I pick now, because when you multiply the 0 matrix by any vector, you're going to get the 0 vector. So x is completely free to be anything it wants, and that would be a solution. If I wrote this in as an augmented matrix, it would look like this. And then taking our knowledge about how to identify the multitude of solutions when you have free variables, notice that no row has a leading 1. And the first column represents the coefficients of x. And because there's no leading 1 there, we know that x is free. And same thing's going to be true for the y column. Both variables are going to be free. So your basic solution to this is going to be the following. I'll say all solutions. It's going to be x could be anything it wants, and y could be anything it wants. And then if you want to break this apart, it would look like the following. X could be anything it wants times 1, 0, and y could be anything it wants times 0, 1. The fact that we have two free variables when I used this eigenvalue negative 2, and negative 2 was repeated twice, so the multiplicity of negative 2 is 2, and we also got the same number of free variables over here, that indicates that when you take your general solution to this system and break it apart this way, that you can see here's a component involving the first free variable, and here is a component of the solution involving the second free variable. And these are the two linearly independent eigenvectors that we're after, because 1, 0 and 0, 1 are linearly independent. One is not a multiple of the other. And so our V1 is going to be 1, 0, and our V2 is going to be 0, 1. These are two linearly independent eigenvectors associated with this eigenvalue. Now that once we have those two eigenvectors, we can construct the general solution. So the first, we're going to do C1 times e to the RT, and R is negative 2, so negative 2t, times the first linearly independent eigenvector, plus C2 e to the same R, so it's still negative 2t, times the second. Now, when I put this general solution together, notice what it reads. It's just going to wind up being C1 e to the negative 2t over C2 e to the negative 2t. So all we have to do is find what C1 and C2 are when I want to find a particular solution. Something else I want to point out about this particular system, because the matrix A was diagonal, remember diagonal means diagonal entries could be whatever, but the non-diagonal, all the entries off of the main diagonal are 0, and this is called the diagonal matrix. And if you were to take this diagonal matrix and rewrite it in the following way, I just want you to observe what's going to happen. So vector x prime is the same thing as saying x prime y prime equals, and then we have negative 2, 0, 0, negative 2 times vector x, which is just xy. So here's our two equations in matrix form. If I multiply this out, notice what it translates as. X prime, y prime equals. The first, I'm going to do the matrix vector multiplication over here. We're going to get negative 2x alone up top, and on the bottom we're going to get negative 2y alone. And when you equate these components, the first one is just a very basic differential equation in terms of x and only involving x. So it's independent from the second equation. The second equation is y prime equals negative 2y. And now the solution to x prime equals negative 2x is a constant times e to the negative 2t. So exactly what we get right there. And then the solution of y prime equals negative 2y is the same thing. It's a constant times e to the negative 2t. All right, these are both very basic separable differential equations, and you can solve them separately because they are not interdependent. Notice there's no y's up here and there's no x's down here. So we have a completely standalone differential equation in terms of x and a complete standalone differential equation in terms of y. You could solve them separately, and you're going to wind up with this same general solution. Just something I wanted to point out. Okay, now the next slide is going to be us finding a particular solution for this. So I'm going to just copy this general solution and bring it down here. And the instructions here are the same. We're going to find the particular solution and then do some graphing. X. So here's our general solution, and now we want to plug 0 in for the t's. That gives me just C1 up top and C2 on the bottom. This is going to be very simple to solve, and we want this to be equal to our initial vector, negative 3, 2. So in other words, C1 is negative 3 and C2 is 2. There's no real system to solve here. And so we can now write our particular solution as a function of t is the following: negative 3 e to the negative 2t and 2 e to the negative 2t. So this is going to be my x function, and this is going to be my y function. And by the way, you could also do some factoring here. You could take out the e to the negative 2t. So there's lots of ways to write these things. You can write your answer this way. It's still just important to remember that negative 3 times e to the negative 2t would be your x function, and 2 times e to the negative 2t would be your y function. Okay, let's go back to Desmos. Let me hide this imagery. Let me hit the home button, go back to our normal scale, and I want to reveal now our x and y as functions of time. So the green is x. So at time 0, we click on the green. At time 0, the x-coordinate is negative 3, and as time goes on to infinity, the x-coordinate approaches 0. You can see the outputs of the green function are approaching 0 as t goes to infinity. And if we focus on the purple function, which represents the y-coordinate, at time 0, the y-coordinate is 2, and also as time approaches infinity, the outputs of the purple function approach 0. So the y also approaches 0. So both x and y approach 0 as t goes to infinity. So in our imagery over here, we would have the x function started at 0, 3 and it approached 0, and the y function started at 0, 2 and approached 0. So this was our y, this was our x function as functions of t. Let's go back to Desmos and hide the functions as functions of time and reveal the point. And okay, so there's the point. My slider must still be at t0. There we go. So we start at the point at time 0. When capital T is 0, we're at the point -3, 2. And as time advances, the solution appears to approach the origin, but slowing down. Because as time goes to infinity, remember the x and y coordinates are approaching 0 asymptotically. So we sort of, in the phase plane portrait here, we see that the solution approaches 0 but slows down, never actually getting there. But this is what the solution does as time goes on to infinity. Okay, so we started at time 0 at the point -3, 2 at time 0. And as time went on to infinity, as time advanced, we approached the origin. It actually approaches the origin linearly because it's easy to eliminate the parameter here, because we know that x is equal to -3e to the -2t and y is equal to 2e to the -2t. I could do a substitution and say something along the lines of e to the -2t is equal to x divided by -3, and then replace that right here. So in other words, together these imply that y is equal to -2/3 of x. So this is the path in the xy plane that this parameterization will follow. So it would really be best if I drew this completely linear, because it's following a linear path as t advances. Okay, let's go to the third example. Suppose again we have a planar, so this is a two-dimensional, homogeneous linear system with an a as constant coefficients. And furthermore, suppose that a has two non-real eigenvalues. So that they're going to be of the form a plus or minus bi. Let v be the complex valued eigenvector associated with r equals a plus bi, where b is bigger than 0. So let's just focus on the eigenvalue, that's the plus, not the a minus bi, and find an eigenvector that goes with it. And then the general solution will be found as follows. So step 1 is going to be, we're going to let z be equal to e to the eigenvalue times t times its eigenvector. So the exact same setup we would do, except now we have complex valued eigenvalues and complex valued eigenvectors. Then step 2 will be where all the work is done. And we'll illustrate that when we get to that point. So first let's begin by finding the eigenvalues of this particular square matrix. So we're going to remove r from the main diagonal. So we have just 0 minus r and 2 minus r. That's my new main diagonal. And we have 1 and -2. Those don't change. Do the determinant of that, set it equal to 0. So multiply the main diagonal, and we're going to get -2r plus r squared. And then remove the product of these entries. So we're going to remove -2. So we're going to add 2. This creates our quadratic equation. Let me reorder things around a little bit. And it is going to have imaginary roots. Let's use the quadratic formula. So r is going to be -b, so opposite of -2 is 2, plus or minus the square root of -2 squared, which is 4, minus 4ac, that's going to be minus an 8, all over a 2a. And this will wind up being r is equal to 1 plus or minus I. Right, because we're going to get a -4 here, and the square root of -4 is 2i, and then 2i over 2 is I, and 2 over 2 is 1. So we get 1 plus or minus I. Now we're going to just focus on the 1 plus I. Let's go with that being our R1. And our goal here is to find an eigenvector, any eigenvector associated with this eigenvalue. So what we're going to do is remove this eigenvalue from the main diagonal. In other words, I'm just going to rewrite this, but with this r in place, and see what that matrix looks like. So change these r's to 1 plus I. I'm going to distribute the negative. So negative r is going to be -1 minus I. And then a 1 over there. And then the bottom row is going to be -2. And then we do 2 minus 1 minus I. That's going to be 1 minus I. And we want to find a vector x here that when I multiply this, I'll get the 0 vector. Now this can be a pain because of the presence of the i's. I did this in the last lecture, but here I'm going to take a shortcut. This can be a pain to put this in reduced row echelon form. But remember, all we have to do is find one non-zero vector here that makes this a true statement. And let's figure out what that vector would be if I multiply to the top row to get a 0, and verify whether if I multiply it to the bottom row, I also get 0. So the obvious choice up here is if I were to put a 1 here, keep this the same, but then put the opposite of this to multiply to this one right here, in other words, 1 plus I, notice that when I take this vector and I drop it down onto here, multiply corresponding entries, so you would get -1 minus I times 1, which is just -1 minus I, plus 1 times 1 plus I, and then combine those results, you're going to zero out. You're going to get this 0 here. So this is a vector that makes the first row true. But we also have to make sure it makes the second row true. So let's just verify when I drop it down here and multiply these. -2 times 1 is -2, and 1 minus I times 1 plus I, that's going to be 1 minus I squared, which is going to be 1 minus -1, which is going to be 2. So we're going to get a -2 here and a 2 here, and when you combine those, sure enough, yes, you get this 0. So I can see that one solution is going to be this eigenvector that we're describing, this V eigenvector, is going to be 1 plus I. Right? These are the components that if they were placed right here and we did this matrix vector multiplication, I would get the 0 vector. Okay, so let me now delete that. Okay, so let's go back up to here. So we have two non-real eigenvalues. We let V be the complex valued eigenvector associated with one of our eigenvalues, the one that has the 1 plus, the A plus BI. We found that eigenvector, and now let's create a vector Z. So this vector Z is going to be equal to E raised to the A plus BI, so this is raised to the 1 plus I times T, and then times this eigenvector that we just found, 1 and then 1 plus I. Okay, so here we are, we finished step 1. Now step 2 is we're going to use this identity. This is called Euler's identity, e to the I theta equals cosine theta plus I sine theta. We've used this in the past to express the above. So we're going to take this vector Z and break it apart in such a way that we have a real component plus I times another real valued component. So you want to get all the i's factored to the front somehow, and we have to use, in order to simplify this part right here, we're going to need to use Euler's identity. So there's going to be lots of manipulation that's going to happen now in order to get to the point where we have a general structure of a real plus I times a real. First thing I'm going to do is distribute the t across those parentheses and then break that sum apart. So in other words, we have that the z vector can be written as e to the t times e to the it times this complex valued vector next to it. Here's where I'm going to use Euler's identity. E to the it is the same thing. So we have an e to the t in the front. E to the it is the same thing as cosine t plus I sine t. So there's Euler's identity being used. Now I'm going to distribute, this all represents a scalar, so I'm going to distribute it to the top and bottom, to the top component and to the bottom component of this vector, and write this as a 2×1 vector. So I'm distributing it across the top, and I'm going to go ahead and also distribute the exponential across these parentheses. So we have e to the t cosine t plus I e to the t sine t. This is what I get when I distribute the e to the t across these, and then I distribute this up to that first entry. Now for the bottom entry, I'm going to not do the foiling. I'm not going to distribute the e just yet. I will leave that separate because I want to foil these two parts first. It doesn't really matter. You could do this a variety of ways, but I'm going to leave the e to the t out for the time being, and I'm going to worry about foiling this with that. So we have cosine t times 1. That gives me cosine t. Then we have cosine t times I there, so we have plus I cosine t. Then we have I sine t times 1, so plus I sine t. And then finally we have I sine t times I. That's going to be I squared sine t. And we're going to use the fact that I squared is negative 1, so I'm going to say cosine t minus. Let's see how this starts to look. So a couple things I'm going to do here. I'm going to distribute the e to the t to here and here. And this is a negative 1. So these parts here don't have I involved anymore. So that's why I'm grouping them together. And the e to the t distributes. So we have e to the t cosine t minus e to the t sine t. And that takes care of this term and this term. Now the other two middle terms here in the middle involve I. So I'll keep them grouped together. So we have plus I e to the t cosine t plus I e to the t sine t. And that should account for everything distributed. And now I'm ready to pull these back apart in such a way that all the non-I parts go in one vector, and then all the I parts, these components here that involve I, will go in a separate vector, and then the I will be factored out. So it's going to look like the following. The first vector is going to be e to the t cosine t, and then in the second component will be e to the t cosine t minus e to the t sine t. You can kind of see why I was tempted to leave all the e to the t's factored out so I don't have to keep writing it, but it is what it is at this point. Plus, now the next one, I do want to factor out the I. Keep in mind that we are trying to express it this way. And notice this way does have the e to the t's factored out, so maybe I should have done that in the first place. I might revise. I'm going to probably revise this. It would have been advisable to have the e to the t's factored out the entire time. But let's just keep moving forward with what I have written. So the next component has the e to the t sine t, and then factoring the i's out of both these parts here, we have e to the t cosine t, e to the t sine t. Okay, I'm going to keep this going, and just for space's sake, let me move a couple of these things around here. I'll move that down there and move all this work up here. And let's call this z. This is the same z we have here, just to create a continuation of our work here. Okay, then I can factor out the e to the t if desired, and I think it is desired to do. So let's factor out the e to the t. Then we have cosine t over in the second component, cosine t minus sine t, plus an I times e to the t times, then we have a sine t, and then a cosine t plus sine t. Okay, notice now we have at some point we used Euler's identity. We used that right when I went from e to the it to cosine t plus I sine t. Then we ultimately were able to express z in the following way. E to the at times some vector. Here's my e to the at, where a is 1, times some vector that does not involve I, plus I times e to the at, so I times e to the t times a second vector. Now our general solution is going to be effectively, we're doing step 3 next. The general solution, if you compare where we're at now and where we're going, the general solution just puts constants in front of this and absorbs this I into that family of constants. So we can go back to real valued by just saying constants in front of these expressions and rewrite this effectively without the I. So this will be an easy thing to do. I'm going to copy paste. The I will go away. This will be now our general solution. We'll have a C1 in front of this one here and a C2 in front of that one, and that's it. We do not need to repeat all of this again with the second eigenvalue of 1 minus I. So for every complex conjugate pair, you just have to take one of them and then go through these motions to get your solution that gives you the two components, or the two linearly independent solutions that you need to combine together to form your general solution. But I do want to copy this now because we're going to do a particular solution for this specific example. So x of t is equal to, and now we want to say x of 0 specifically. At time 0, let's see what we get. And I'm going to do a lot of distributing here as well. So I'm going to not only plug in 0 for all the t's, but I'm going to distribute. Well, let's do this in 2 steps. I just don't want to do too much at once. So we have a c1 in front. E to the 0 is 0. Cosine of 0 is 1. So we have a 1 up there. Sine of 0 is 0. Cosine of 0 is 1. So we have a 1 down there as well. And, okay, looks good. Plus, in the second vector, c2, e to the 0 is 1. So that we don't need to write that. The sine of 0 is 0. And cosine of 0 is 1, so we get a 1 down there. So we want this to ultimately be the 1, 2 vector. Well, if I combine all this into one vector, what would that read as? It would be c1 plus no c2. It would just be c1 up top. And the bottom would be c1 plus c2. And we want this to be equal to 1, 2. Well, this tells me that c1 has to be 1. And c2, therefore, is going to have to also be 1. It's a rather simple system to solve. There's c1, and now that I know that c1 is 1 and I want these to add to be 2, I know what c2 is. So I'm able now to write my particular solution, and I'm going to write my particular solution with everything I'm going to group all this together into one vector. So we know that's a 1 and that's a 1. And so we can distribute e to the t times cosine and e to the t times sine and add those together. So our first component will be e to the t times cosine, and the second will be term of this first component will be e to the t times sine t. So there's our x function. Now let's look at the y function. Remember the c's, these are 1 and 1, so that's easy to keep track of. So we just have to distribute e to the t across here, and then e to the t across there, and then add those together. So we're going to e to the t times cosine t. There's going to be another e to the t times cosine t. So we'll have 2 e to the t's cosine t. And then we're going to have e to the t times negative sine t, but e to the t times positive sine t. So they're going to cancel each other. So that's all we get for our second component. And here is what we want to graph using technology. So switching back to Desmos, let's hide the F2 and G2 information. And here I've already typed in my F3. That's my x function as a function of t. I have the e to the t factored out, but that's okay. And then here's my y function as a function of t. And here they are plotted together. So you can do your best over here to make some sort of picture that mimics that. I'm going to do this, rather lazily, but, make it look better, but copy your work over and put something here in your guided notes. We would delete that. And then now we want to do the phase plane plot. So I'm going to hide the functions of t, put them together as an ordered pair, reveal the point, and then let's go back up here and zoom out a little bit. And so we start at the point. Now be careful here, these scales are off. Let me hit the home button. There we go. So we start at the point 1, 2, and then as time goes on to infinity, I have time stopping at capital 2, but you start to see a pattern emerge. Feel free to change this upper limit of capital T to larger numbers, and thereby seeing more of the curve as time goes on to infinity. In fact, why don't we do t to 20, drag it all out to 20, and just kind of zoom out and see if we can see any sort of pattern here. Interesting. As I zoom out, it looks like we have, oh, how interesting. It looks like we have some sort of spiral happening that's really zooming away from the origin. Very interesting. So we get the motions of a spiral dramatically getting further and further away from the origin and continuing to spiral. Okay, so we started at 1, 2 right here, and then we had some sort of spiral thing. Oops, the arrows matter. Some sort of, this was at time 0 where we started, and we move in that clockwise direction. Okay, and this concludes this topic 26 lecture on linear planar homogeneous systems of ODEs.